I selected this pretty picture, just struck my attention. It's just a NASA archive picture a few days ago. You might have seen it. Well, it is a nice picture, but just got my attention because also the ultimate objective for us, in radio transients is to understand the radio transient sky, as well as we would understand, say, some of the other wavelengths. And so basically a comprehensive exploration of radio transients. That's what we are essentially after. So I'm going to cover a bit of background and introduction. And like I said, there's a lot of people working on transients here, and they would probably find it boring. But for those who may not know a whole lot, will probably find it useful to get a picture of what it is like. And then highlight a few interesting outcomes from high time resolution surveys that are going on at Parkes and Arecibo. Not everything about those surveys, because those are basically pulsar surveys, but just some transient related science outcomes. Then talk a bit about the way we go about searching for these transients, at least the kind of methodologies the way we follow on single dishes. And when you move on to arrays, you will need to make quite a few changes, but at least tell you how things are approached for the searches that are being done with the single dishes. And also talk a little bit about some of the targeted searches. It's an interesting application of transient detection. If you are after finding pulsars in far away galaxy, and that is one of your most promising techniques. So I will just briefly mention, and one such project I just wrapped up a few months ago, and then finally cover a bit of GMRT based effort where we are basically equipping that instrument to some transient detection, pretty much along as like that learning exercise for transients with pathfinders and SK and so on. Okay, so tell you very briefly, and it is a very major topic in radio astronomy these days, and practically every instrument and every pathfinder and all instruments want to do that, and for very obvious reason, because these are like very energetic and dynamic events in the universe, and we know from the past several years of research that you can have like a phenomena that last for like a billionth of a second to something which goes on for like months or years, like supernovas and gamma ray bursts or whatever. So you do these things routinely, and but especially at a higher energies, you understand the transient sky much better, and that's because you have had very good instruments, space-based instruments with which can monitor a large part of the sky. And for a long time, radio astronomy did not enjoy that luxury, and that is one of the the technological barrier. You never had instruments that could look up a large part of the sky, and that's what is going to change very soon. All these pathfinders like ASCAP and the low frequency arrays and MWA and everything will have like very wide field of view. So you will be able to monitor the sky it's a large part of the sky, and that's what is basically going to help you in finding these events which last only for like a small duration of time. Other thing I must mention that when you talk about studying transients of very short time scales, like milliseconds or microseconds, and that is when you have like a whole bunch of technical challenges. You need to worry about things like a dispersion and scattering, which is all due to the intervening media between the telescope and the source. It could be the intergalactic medium, interstellar medium, or whatever. So they can distort the signal, so you have to address them one way or the other way, which translate to a lot of computations. You need to sample the data very fast. You need to have very high time and frequency resolution, so your data rates and volumes will be pretty high. Then of course, that radio frequency interference is the biggest challenge over here. So the combination of all those things translate to a lot of computations. I must also mention that when all these developments are underway, that interesting discoveries are being made with the existing telescope, and I will just highlight a few of them in a short while. And just to give an idea for those who don't have the distinction clear about the slow versus fast transients in radio. Basically, the slow transients are the things which you can detect, say, in doing some sort of a raster scan and imaging from snapshot to like daily, weekly, or whatever. So things like supernovae or gamma ray bursts, they are all like so-called slow transients. And things which last for like microseconds or nanoseconds, like giant pulses from Pulsar. So you need to sample the data at a high time and frequency resolution, and you need a time domain processing. So you can just call them as like fast transient. So I mean, the distinction is not very well defined. So basically anything that involves time domain processing, it's sort of a fast transient, and things which you would do using other techniques can be slow. Like I said, that I'm going to focus pretty much on fast transients, because as a pulsar astronomer, there is a lot of synergy between fast transients and the way you do pulsar processing. So you can see that lots of pulsarists turning into transient researchers like Steve and me and JP and so. Anyway, so just to highlight a few important discoveries of recent years, and some of you may know this, the Galactic Center Radio Transient, which shows some sort of a quasi-periodic emission, and the VLA archival data, the reprocessing of which revealed some faint Millijansky sources, which it's not still quite clear what is going on. And this is Parkes multi-beam discovery, original Parkes multi-beam survey, and these are called rotating radio transients. It's basically a class of neutron stars which you would find not using the standard periodicity searches, but by looking for individual pulses which are dispersed. They're called rotating radio transients. And although you can argue whether that was the right name to associate for this class of objects. Then the transient emission from some of the magnetars, because a few magnetars, at least 3 are known, and when they become active, they tend to give a very powerful burst of radio emission. You can just see it in single pulsars with even telescopes like Parkes, and in fact Parkes found all 3 of them. Then this single one-off event, so-called Lorimer burst, and which created a lot of speculation for quite some time, and now we understand what is probably it's not likely to be astrophysical, but whatever it may be, that all these discoveries have had an important outcome, at least in the way the pulsar people do searching. So searching for fast transients is pretty much part of the survey strategy these days. And so at the moment, there are 2 major higher time resolution surveys are underway, one using Parkes and other using Arecibo. Both use multi-beam receivers built by CSIRO. And the Parkes multi-beam receiver has been around for like past 20 years. But the big difference is that now you have got a new digital backend. So you can sample the data almost 4 times faster and 10 times higher in spectral resolution. That is the kind of instrumentation you have at Arecibo as well. So these surveys can look at, or they are sensitive to millisecond pulsars at very large distances. So in terms of finding pulsars, these 2 surveys are not doing as good as the original multi-beam survey. They probably won't. But if you look at the rate of discovering millisecond pulsars, I mean far away millisecond pulsars, and in particular finding the transient emitters. When I say transient emitters, most of these are essentially rotating radio transients. They have been doing pretty good. And of course, every once in a while, you have interesting special targets like relativistic binaries and magnetars. And you must have also heard about so-called diamond planet pulsar recently. Anyway, so important thing is that, that it has become a pretty routine that for all pulsar surveys, data are processed for searching fast transients. Well, means finding a bunch of objects is one thing, and scientifically, what does it tell you? And just going to show a couple of plots, and this is just a summary of so-called rotating transients discovered with Parkes and all other telescopes so far, and all the pulsars that tend to null. So you can see that this is what is plotted here is the duration, the fractional time in which it will be emitting into normalized to whatever, the observing length versus the mean of time. And of course, it's not very conclusive, but you can see that, that if you compare, there is some sort of a pattern evolving here when you put together the non-nulling pulsars and the rotating transients. So it's quite possible that, the rotating transients are basically, one case of nulling, or at least there may be some connection. So basically, you have to understand the intermittency as the whole thing. There is another interesting summary, and this is all the objects for which you could assess the search detection using transient searches as well as periodicity searches, and what is plotted here is the ratio. So if something is above 1, means those objects are easily detectable through transient searches. And so you can, and the different curves plotted here are like a different intrinsic amplitude distributions. So it can help you to understand what sort of objects are potentially more easily detectable through transient searches. Well, the number of samples are not very many at this point, but the projection is that, if you continue such search strategies, you can be discovering a large population of them. At least that's one distinct class of neutron stars that tend to emit every once in a while. Just to sum it up, so all that you have known so far, in at least in the radio transients, like the giant pulsars and rotating transients and magnetars and so on. So if you put together in this so-called phase space plot, which is from Jim Cordes, and it combines all the known phenomena into a single plot, and it's essentially a plot of peak flux density multiplied by distance squared, which is the luminosity, and some sort of a luminosity, and versus a frequency multiplied by pulse width. And one important thing to take from this plot is that unless you assume that nature has its own preference, you have to conclude that there is a large part of the parameter space that is still unexplored. In other words, there is a lot of discovery potential in this area. And that is obviously the driving factor for pursuing this science with a lot of new instruments. So let me just briefly cover some of the important things come into play when you start looking for this sort of things. And obviously, things like detection sensitivity, survey speed, and the volume that you sample, that is an important factor. And like I said, you need to worry about things like propagation effects like dispersion and scattering. I will describe them in a minute. Then you need to search over a large range of parameter space. It is not just the range of the parameter space. You also need to have like a very high sampling, very high resolution sampling. And if you have to detect a maximum number of signals, radio frequency interference is a big problem. And of course, that as we move on to the new instruments, you need to develop newer strategies and algorithms. And I'm sure that some people in this room have thought about some of this a lot more extensively, like JP has worked on some of these factors and how they should be optimized for upcoming instruments. Let me just quickly go over some of the more basics. So essentially, for any given instrument, your minimum detectable flux density is an important factor. That basically defines how far you can be looking at. It's pretty much decided by the system sensitivity, raw collecting area, and the performance of the receiver. Because this is one sort of a science where you don't gain from observing longer, because it is a short duration phenomena. So your sensitivity is pretty much defined by the length of that event. So you primarily gain from having a big telescope and more bandwidth and better receiver. That's all. But it's important to recognize that there are lots of instrumental and other effects come into play. For instance, you will be obviously, sampling the data at finite time resolution. So which means any signal that is shorter than that will be instrumentally broadened. Then you also will have like some amount of a smearing effect coming depending on how you are sampling in the dispersion measure. And of course, at some frequencies, low frequencies especially, And also when you look more towards the galactic plane or towards the center, so you can have like a further kind of propagation effects, like smearing of the pulse due to so-called multi-path scattering or pulse broadening. So in the end, all this is going to basically broaden the signal, which means your signal amplitude will be degraded. Effectively, your maximum distance to which you can look will be reduced, and so is the search volume. And of course, then there is a survey speed, then which is the maximum instantaneous sky that you can see at a given time, and all these things into factor into so-called figure of merit for surveys. And this is just an example of how Dmax scales with intrinsic luminosity for Parkes and Arecibo. So when these sort of effects are not important, you will see that pretty much the Dmax will scale with the luminosity in a linear way. But once one of those effects kick in, then your searches will be either dispersion limited or scattering limited, depending on your instrumental design. Okay, so very briefly, I'm just going to tell you some of the important effects that you need to worry about. One is the dispersion and the intervening media. I'm just saying this as an interstellar medium as an example, where you will have free electrons, so which means there will be frequency dependent index of refraction. So the radio waves, as they go through, they are going to travel at different speeds. So when they reach the telescope, they will have like different arrival times. And this is what basically the dispersion. So when you look at the signal, so you will see that there is a range of arrival times. And if you don't correct for that, the signal is going to be smeared. So when the signal is really bright, you can see it, but most of the time that is not the case. Signal will be well buried under the noise. So you have to correct for this effect. And but if you don't know what the dispersion measure, in other words, you don't know where the source is, so then you have to trial a large range of, large number of DMs. And that is where the computation comes in. Even at small bandwidth at low frequencies, you have to go to like thousands of DMs if you want to sample the dispersion measure space optimally. And the way we do that, typically in the searches, the way we would do that is just sample the data at very high time and frequency resolution. Then for various slopes, which is various dispersion measures, you can shift and align and add the signal, then see if there is a detectable signal there. And that is called incoherent dispersion. And the important thing to realize here is that for every time sample, for every DM, you have to perform so many computations. And if you have the large number of data streams, which is what will be the consequence when you move on to multi-element instruments, this becomes quite large. So you are talking about like a multi-tera operations per second, even for small bandwidth using array-like instruments. So this is the computationally, challenging part of this one. If you can address this, I think you are pretty much on your way. So I'm just giving an example how we have been doing this with non-single dishes, like large single dishes like Arecibo and Parkes. So basically you search in the dispersion measure and in the time domain, but to detect the signal you use so-called match filtering. So which is essentially in some sense, like looking for like different pulse shapes, but in practice, we don't do anything that complicated, but we essentially sample the data at different levels of time resolution and see if there is a signal. And when you do that, so anything that is astrophysical will have a very distinct signature, like it will peak at the true DM of the signal, and when you move away from DM, so you will have like signal strength falling off rapidly, and that's what you will call it like an astrophysical event. And that is pretty much you can do when it comes to searching with single dishes, because it doesn't give you a lot of leverage. This is one of the cleanest data sets, not all the time that is the case. And so just to sum it up, that a few different techniques that are commonly used, that apart from the match filter, and which is quite useful, and in the sense that it gives you the increase in sensitivity. But oftentimes, that it is not very effective when you have like a weak broad signals. And that is where you try different approaches like, the time domain clustering, like basically finding an event, then look for the associated events using some sort of a friends of friends kind of a logic. like used in galaxy searches and so on. So the two have both pros and cons, and this is just an example of match filtering, and this is an example of the same data going through a friends of friends kind of a logic. So you can see that in friends of friends logic, then the number of RFI events, pretty much, the spurious events, it could be RFI, it could be the noise statistics or whatever, and they cut down quite heavily. So that is one of the advantages. Whereas when you look at the match filtering, then you essentially can build up the sensitivity depending on, at least for the broad signals, you can gain in sensitivity. In time domain clustering, you are just limited by the sensitivity that can be provided by the sampling resolution. So in some sense, two are complementary, and we routinely use them for any Arecibo-based searches and even for the other telescopes. And I must also mention that there are other techniques being developed and experimented using VLBA-based efforts, and those are not really tested and tried for large surveys like this. But it's important to recognize that this is probably not the only way of doing it. Yes. Okay, RFI is a big problem, and people who are working on transients will appreciate that very quickly. And just to make that point quite evident, so here is just a data where supposedly a bright, very powerful giant pulse is hiding inside the data, but just can't see it because it is so masked by such a dense RFI forest. So when there is RFI can be powerful and impulsive, even dispersed signals can be totally masked. And so that's basically one of the biggest problems. And the RFI can come in the whole kind of variety. You can have like things which is there for all the time, or things which is there over a large range in frequency, or certain things can be narrow band, or certain things will be just impulsive and whatever. So there's no simple rule to get rid of them. And for instruments like ASCAP and MWA are advantageous in the sense that you have got the best sight in the world, but most of the instruments, RFI is a big problem, and you have to that battle against it, and if you are going to find something sensible in transient searches. So this is just a simple algorithm just to illustrate that that you can have like a large bunch of RFIs in the data. So, but the key to work around the RFI is that it says it is possible for RFI to mimic some of the signatures of astrophysical signal, at least in the time frequency space. But it may not be that easy in when you start characterizing your observational space in terms of location and direction. So basically any signal, especially when you have multiple instruments or multiple pixels or whatever, you can characterize it as a function of the location and direction and time and frequency. So RFI and the celestial signatures might have a similar signature in time and frequency sometimes, but it's very unlikely that they will share similar signature, at least a good part of the time, in both in direction and location. So in essentially, RFI can be very site specific and depends on the directions. So if you, by using this directionality and the location, so you can use the effective use of coincidence or anti-coincidence, whichever works out depending on the instrument and the problem, and to discriminate between the RFI generated events and the signals. And that is basically the principle behind using multi-beam receivers and multi-station receivers and so on. So how well you can use it, that basically holds how successfully you can look for these sort of events. So just to give you an example, this is Arecibo multi-beam receiver. So Arecibo has a multi-pixel receivers with 7 beams which can point to adjacent part of the sky. And this is just those bunch of plots that I showed earlier, but for each and every beam. And so when there is a signal, the signature will be very clear if it is very bright. And you would think that the RFI should typically be seen through all the beams, which is generally true, but not when you have like a very complex optics like Arecibo. Arecibo has like a primary mirror, then there is a secondary mirror and third mirror. So depending on how the signal bounces around, So you can have like situations that RFI coming through either 2 or 4 or 5 or whatever. So automating algorithms for 100% RFI removal is not very easy in those cases. But you can still develop essentially, saying that if signal appears in many beams, it is likely to be not astrophysical. Well, at the end, there is nothing like going back to your data and scrutinizing it. And, the same thing that, comes up as like a challenging in terms of computation, like dispersion and scattering and other propagation effects like scintillation can also help you in, as serving as like important integrity checks. If you find a signal that's appearing only in one beam, and if it has like a very clear dispersion signature, and if the signal falls off the way you would expect, for that sort of a dispersion measure. And this is a nice example where you can even see the structure across the frequency, which is due to another propagation effect known as scintillation. And if you know the DM and if you know the direction, you can make some sensible predictions and compare. So you can very quickly verify, whether something is astrophysical or not. And this is another example. This is using Park's multi-beam receiver, and it's a weaker signal. And so apart from verifying that signal is seen only in one or a few beams, because sometimes the source may not be exactly aligned into one beam direction. So if the beam source is offset, then it can be picked up by the adjacent pixels as well. But if you see a signal peak in a dispersion measure and as well as so-called match filter time resolution, and you know that is going to be likely real. So you need to look at the whole bunch of criteria before you declare that it is a signal. Of course, in the case of rotating transients, signals will repeat at some interval, so that repeatability is also like your advantage. But often, or sometimes, you may not have that sort of a situation. And so these are the important checks you can do. So I will very briefly mention this another propagation effect, which of course we don't worry about it in the current searches with Arecibo Parks, but there's something which definitely you have to keep in mind, especially at low frequency instruments like LOFR and MW and GMRT. And also if you want to get your optimal sensitivity back, at least if you want to optimize the searches to shoot the galactic propagation effects, this is something which you have to bear in mind. So basically, if the source is compact, quite often it can be compact because the fast transients, the transients are generally associated to compact sources. So the signals can be like scattered into multiple different directions, and so they will be spread of arrival times. So in effect, basically the emitted pulse gets convolved with what is called the pulse broadening function. So they will be smearing of the signal. So it will get stretched and it will get sort of distorted. So this is an effect that sort of degrades your sensitivity in some sense. And so depending on the way the material is distributed or organized, you can have like a variety of pulse broadening functions that can distort the signal. And even when the signal is not really, the smearing is not easily visible in the data, you can still see that effect as a modulation of the signal across the frequency or in time. So this is an effect which is there in your data one way or the other way. So by optimizing your strategies, you can, that increase your sensitivity for transient searches. And this is an effect that varies quite dramatically, when you move to the galactic plane or towards the center or to low frequencies. This is a very, very predominant effect. But if you are sticking like, higher frequency or, that away from the plane, this is not such a big issue. So you can work out some sort of an empirical relation based on your observational data, but this is an effect that you have to factor into devising your strategies, search strategies. And especially for next generation instruments where the field of view is going to be larger and you want to that maximize your detection chances And this is an important effect that has to be factored in. And JP has done a lot of work in this area recently. So I just mentioned it because it is something that have to be factored into any searches with the low frequency instruments like GMRT and MW and so on. Okay, so before I move on to what we do with the GMRT, let me briefly mention one of the interesting application. And if you want to find pulsars at far away galaxies, like the nearby spiral galaxies like M33, which is about a megaparsec distance, which is almost 100 times far away compared to the typical distances that you normally search for pulsars. So obviously, the detection sensitivity is your the ultimate key. So even with Arecibo, and it's very difficult to find even the most luminous pulsars at that distances. Arecibo does reach something like a few microjansky sensitive in a couple of hours of time integration. But even if you take the most luminous pulsars at that distances, they are barely detectable. So you have some chance, but not very easy. But if you look for like transients, the very powerful transients like giant pulsars, which can be like thousands of Jansky or some tens of kilojansky, then you have some chance in finding such signals at that distances. So most recently, that we just completed processing of a huge amount of data, and there's a systematic survey of the entire M33 using Arecibo multi-beam receiver. So it's pretty much like that huge amount of data and a lot of processing, thorough processing, and there's a multi-beam receiver, so it gives you a lot of advantage in finding something, whether it is real or not. And that is exactly what many of the previous searchers didn't have. They used to find candidates, but you could never verify. So we haven't found anything. Any transient emitting objects like magnetars and rotating transients, if you take it to that sort of a distances, you can see that this is Arecibo sensitivity. They are way below that. And talking about the giant pulsars, you have some advantage. They are just at the borderline of sensitivity. So if you have crab-like pulsars, and at least in the on the face-on side of this galaxy, you can hope to detect them. And we have searched through the whole data, and we have had hundreds of candidates, but none of them finally turned out to be real. And but so even when the new instruments come up, and these are some of the applications where the large single dish sensitivity will still hold as the main factor for the success. Anyway, so where do you go from here? So there are a whole bunch of future instruments, and some of them will have higher sensitivity, like this large aperture fast telescope coming up in China. Of course, whenever you can't do anything, and the SKA is the final ultimate answer, SKA can do it. Anything you can't do now, SKA can do it. And with the newer backends, Arecibo will have much better chances. At the moment, you just about like the detection threshold when you have the most optimistic scenario. And SKA phase 1 will have a very similar sensitivity, but the biggest advantage with that sort of an instrument is that it will be able to look at many more targets than Arecibo. Arecibo's sky visibility is restricted, so you don't have many targets to choose from. Just to amplify on that point a little bit, and so this is some compact array observations that Stephen and I did some time ago, and so this is at a very high time resolution, looking at giant pulsars at the microseconds kind of a resolution. So if you translate that to the nearby galaxy distances like the M33 and some other dwarf spheroidal kind of a galaxies, and you can see that that there is some detection prospects out there if you search with the new instrumentation at Arecibo. So the one way of doing it is just with the newer instruments and find the better targets and keep going. And the other way of approaching this problem is that these are the signals which has like a very steep spectrum. So when you go to low frequencies, your detection prospects are naturally, increased because of the steep spectrum. So you need to understand how the spectrum and the rates of giant pulsars behave at low frequencies. And that's one of the projects which we are doing at the GMRT. We have data simultaneously taken at multiple different frequencies, because characterizing giant pulsar spectra can be quite non-trivial, because oftentimes you don't find same giant pulsars coming through all frequencies. So, but understanding, how often such bright giant pulsars come and how their spectra behaves and how propagation effects come into play can give you some insights into what prospects you can have with instruments like LOFAR and MWA to do such searches. Okay, so coming to the second part of my talk, and like I said, that pretty much all new instruments are, interested in doing transients. So we do them with the single dishes, and VLBA has a transient exploration program that's going on, and so the GMRT has some nice features that you can use to develop transient capabilities. And of course, wild field instruments like ASCAP and LOFAR has major key science projects in this area. The reason why I put up some such table is just to make the point that practically every instrument has an important role to play. Like I said, that when it comes to detection sensitivity, there is nothing like Arecibo. So anything where the detection sensitivity has to be the, the main thing, Arecibo will remain your best bet in the foreseeable future. And the VLBA has the fantastic resolution when it comes to pinpointing, if the event is real, in terms of localizing, the VLBA can give you like a milli-arcsecond resolution. And ASCAP and GMRT can give you something like, a few arcseconds resolution, which is not very bad, but at the same time, the fact that, such a capability did not exist at all for a long time, that's a very major plus. And of course, that in terms of field of view, that next generation instruments win over everything else. So there's ongoing surveys with instruments like a GBT and Arecibo and Parkes, and VLBA and GMRT are trying to use that multi-station and advantage to work against RFI related events, and also to localize the events through their imaging capabilities. And things like LOFAR and ASCAP will offer you a lot more. They will have multiple pixels and multiple stations and large number of other advantages. So, well, GMRT is not an instrument that's specifically designed for transients, but it has got some nice features that you can capitalize in to do some useful exploratory work. Like, it has a pretty good collecting area, Means anything that you do with the GMRT can be like a very sensitive explorations, because aggregate collecting area of GMRT is like almost 3%. But you don't have to worry about like thousands of data streams, which is one of the biggest challenge in ASCAP. You only have like 30 elements and not very large, the baselines are pretty moderate but not very long, but 25 kilometers baselines are pretty good for localization. And you have a new backend which basically take the data from each and every antenna and polarization and do most of the computations in the software. And that backend has a lot of flexible modes that you can tap and work with the data. And so basically, that your bandwidth is not very high, it's about 32 megahertz. Your number of data streams are not very large, but you still have like a good collecting area. And it has a lot of flexibility in the way you want to configure. There's a very flexible subarraying kind of a capabilities that you can play with. So the combination of these makes it like a very good platform for developing and testing some of the new methodologies that you will need for next generation kind of an instrument. Oh, well, this is basically, that, how much suppression you get against false positives due to noise statistics. And it has nothing to do with the detection sensitivity. It's pretty much, that how things will scale depending on the number of independent elements that you will be checking against. And if you combine the signals, you can do it in two different ways. You can detect and combine, which is called the incoherent combination, or you can basically add the signals in phase, which is like a coherent or phased array kind of a mode. So the incoherent combination retains your field of view, and it also buys you some sensitivity. So you can work out this. The other possibility is like the dividing into multiple groups. So you will have some sort of a trade-off in terms of sensitivity and checking for false positives. So these plots are not very obvious in what they mean to say, but the bottom line is that you don't need to have very many subarrays to build resilience against false positives. Something like 4 or 5 subarrays is all that you need. So you get pretty much good part of your deal if you just divide things into like 4 subarrays. Those of you who may have used GMRT or who know about it will recognize that it's basically a VLA like an instrument with the 3 arms. So, and naturally that the antennas which are located at the center, which is close to the central electronics building, will have a lot more local RFI. And from experience, we know that the load of RFI tends to vary across the array. And things which are local to one of the arms oftentimes don't appear or appear at much lower intensity. So you can make use of that as your important consideration. So basically that it's a natural way of splitting the array will be like just dividing into like the 3 arms, and the central group forms like a different subarray. So the combination of that sort of a flexible advantages and the fact that with the software backend you can get the raw voltage data from practically every element, so you can just play with it as you like. It gives you enormous flexibility to play with it offline. So the plan we have in mind is that the software backend has pretty much everything that is required for data collection and processing and correlation and things like that. And the lots of those libraries and software is sort of tailored to produce this multiple subarray data streams, because it is a heavily optimized computing software. So you have quite a extra computing resources at your disposal, and that you can use using a similar kind of a technique to produce multiple data streams at the same time that you are basically using doing any other observation. In other words, you can just do it commensally and real time. So without any problems, you can generate multiple subarray data streams at the same time the instrument is doing whatever is standard, whatever other kind of observing mode. And the idea is that that you basically add on to the transient processing and other kind of resources just to do that. And there is a paper that describes the details of implementation of the software backend. So what are the main advantages of such an experiment? It's pretty much similar to things like a VLBA based experiments will have, in the sense that you have a long baselines. Well, not as long as like VLBA has, like thousands of kilometers, but even then the lots of local RFI can be suppressed or eliminated, as I will show in a short while, using that multiple subarrays that are carefully chosen to develop resilience against RFI. You can achieve something like 5 to 10 arc seconds imaging resolution at GMRT frequencies, so which is quite similar to the imaging resolution that ASCAP also will have. So that is pretty good, and so you can localize if you find something. So you have the advantage that you can capture that data and go and image it and see if it is something from the sky, because it's very difficult for a terrestrial RFI to mimic a point source or some sort of a sensible source in the imaging thing. So you can take advantage of that. Then of course, once you know that, okay, this is where the source is and this is the likely candidate, you can use the same machinery and go back and form a sensitive phased array towards that target and get back your sensitivity of full phased array sensitivity. So which is almost like 10 times higher, given the fact that you do an incoherent combination and subarraying. So you get like a big boost in sensitivity, and that itself is your major integrity check. So like I said, that GMRT gives you like a few square degree field of view, and it is not an instrument meant for like a big surveys of this sort. So you just that have a strategy that just alongside whatever observations that are going on, you will collect the data and keep looking for the transients, and pretty much similar to the way VLBA based transient exploration is working. So this is all part of a bigger collaboration effort because there is multiple different goals that developing this transient detection is one thing, and we also have like projects that aimed at developing a high time resolution capabilities for Pulsar with GMRT, and of course demonstrating a VLBI between GMRT and long baseline array. And so you must have heard about it because Randall and Stephen have been leading this effort, and they have successfully demonstrated that it can be done. So this is pretty much the way we do, and you, like I said, the capture raw data and form multiple subarrays, and you do whatever your RFI mitigation and quality checks. At the moment, we just do some very basic quality checks to make sure that the data is like sensible and it's not corrupted by any instrumental malfunctioning or whatever. Then you do your searching, and once you find that there is a candidate event after your coincidence, you generate a trigger, and that trigger basically that alerts the recording system to save that data checkment. Could be like about a few seconds, and for further detailed scrutiny. So that is when you go and do things like imaging and phasing and all kinds of things. So this is a very simple flow diagrams that how it works. So you form the whole array into like multiple groupings, and so depending on the number of subarrays that you generate, you can have like multiple parallel search engines, each one operating on the single subarray data stream, and doing de-dispersion and transient searching all in real time. And then once you find the event, and you just that alert the recording system to save that data for further scrutiny. So we did a survey of a small region of the sky, and not using this particular mode, but essentially to collect the data that can feed back into developing all those processing and analysis pipeline. So we just covered something like about a 400 square degree on part of the sky where you think, that already there are non-transient emitters exist. And you tailor the strategy just to shoot the scattering, which I described some time ago, and collect the data all in raw dump. So it's like almost like 200 terabytes of data, even for like 50 hours of observing. And these are the data that we are using for developing all this detection logic and pipelines and analysis, event analysis strategies and so on. So in terms of processing pipeline, this is essentially what we do, and the same thing that I showed before, but in a little bit more details. So, and apart from showing some extra information that is required before and after, this doesn't say anything too much, so I might as well skip it. So just showing you some examples from this transient detection pipeline. And like I said, that you can, once you record the data, you have an enormous level of flexibility to form as many subarrays as you want, like 30 or 10 or 15 or whatever. So this is probably one of the extreme case where every single dish is like effectively like a subarray. So the principle here is that, that if you find something that is showing up in each and every subarrays, you will just consider that as like likely to be an astrophysical signal. But of course, you will be looking for the frequency time signature where you should be seeing a dispersion, and the signal strength should change as a function of DM the way it should. And if it is something due to local RFI, which could be narrow band or broadband or whatever, so it can have like a completely different signature. So they won't show up in the coincidence logic. And this coincidence logic appears to be very simple, but in reality, it may not be that simple, because when you form multiple subarrays, keep in mind that, that every telescope has its own, that baseline variations and gain variations. So you have to factor all that into account when you apply the coincidence logic. That can change into like the difference in the signal detector signal characteristics, or even DM. So depending on the sensitivity variation across the subarray, so your coincidence logic has to be like flexible and adaptable. Otherwise, you can miss out the signals. And so this is just one more straightforward example, but RFI can vary quite dramatically. And I have more examples, but I won't put them up over here. So for most of the processing that we do for the survey data, and we just divide the whole array into like 4 subarrays of nearly equal sensitivities. And the subarrays are grouped in such a way that you can take best advantage of the RFI environment across the array. So this is from 4 different subarrays showing the time series and as well as the frequency time sweep and so on. And this is the true DM, and this is the DM high and low, and this is the 0 DM. So if the signal appears at the maximum at its true DM, and if it shows like the reduced strength as others, and if you can see signatures in all 4 subarrays, that is when you will say that it's likely to be astrophysical signal. I'm just showing you another example just to show how far this pipeline can be pushed. This is an example where the single antenna, which is like that's the the maximum you can push in terms of the sensitivity, and you are sampling the data as like 30 microseconds. So even this is like the single giant pulse that was observed by emulating some sort of a survey mode, in the sense that you just scan the telescope at some sort of a half a degree per minute, and the beam width is half a degree. So typically within 1 minute, crab giant pulse can be emitting like at the most 1 detectable bright giant pulse. So since you are scanning, the pulsar will be within the beam just once. So this is basically pushes all the limits of our observing strategies and configuration. And the fact that even few percentage departure from your signal can lose the sensitivity by like a factor of 4. So it just summarizes that you need to go for very high time and frequency resolutions and very high sampling in dispersion measure, and so it's all translate to like the fairly significant amount of computations for low frequency searches. So we have a GPU version of the de-dispersion software. It's developed by Ben Barstow at Swinburne. And for the kind of typical time blocks that we intend to process with this pipeline, you can see that at least for the bandwidths that we are interested in at the moment, like 32 megahertz, you can happily do it all in real time. So there is no major computational challenge anymore. Once you just these are all like a single Tesla card. For 32 megahertz bandwidth for this sort of software strategy, you can happily do that just within a single card. So if you have like the 4 or 6, 8 of them, you can do it for like that transient detection pipeline in the way we have actually planned. The important question is that how often you are going to encounter spurious events, because every time you encounter a spurious event, you will be recording the data, and it's all raw data. So even if you detect like that some several thousands of them, very quickly you can build up the data volume, and all these data bits have to go through a very detailed event analysis pipeline. So obviously you will be limited by your computational and data storage resources. And this is just an exercise, that it's a little complicated plot. Basically it shows the event rate as a function of detection threshold, as well as a function of subarraying kind of an option, going from 15 different subarrays to like 2 different subarrays. That is the best you can push it to. So the top curves basically shows the event rates for single subarray, and bottom ones are like the different combinations of subarrays as a function of the threshold. So the two important bits to take from this plot is that whenever there is a real signal, of course that your detection prospects will be determined by your threshold. But you can pretty much detect all of them, in the sense that any detectable event can happily sail through the kind of coincidence filter logic that we have. And this is a typical scan when there is a RFI is like what I would say like a the moderate, not very high or not very low, but the normal kind of a situation. So the kind of thresholds that we hope to work with is about like a 5 sigma threshold for 4 different groupings of the array. So you can see that the trigger rate is going to be like well less than once every 20 seconds, and so which is not pretty bad. With that sort of a duty cycle, you can sustain this sort of a search strategy for like 24/7 kind of a mode. Okay, so now the last bit, that what do we do once you find these candidate events. And so this basically shows the scheme that we have. So things may not be readable there, as I was guessing. So that's why I sort of blew it up. This is the first half. So your database basically keeps track of all your calibration data and collects all the raw data segments from recording system and the full information about the candidates. Then depending on the characteristics of the signal, how strong it is and how broad it is. So you will have to resort to either an imaging and as a way of localizing it, or sometimes that if with the kind of software you have at the moment, you cannot produce very high resolution visibilities, and in those other situations you might have to try time domain kind of a processing, where producing multiple beams across the field of view, then use coincidence tests pretty much like you will do with things like Parkes multi-beam or Arecibo multi-beam receiver. So assuming that you can localize it one way or the other way, then you go back and form a sensitive phased array towards that target. And then, and again, depending on what sort of signal it is, you can be doing like an incoherent de-dispersion and detection and other checks. Or you can be doing like coherent de-dispersion if that signal requires that phase coherent de-dispersion to get the maximum out of it. So that is all the information that goes into the final candidate scrutiny, and then those are the events that you further follow it up with whatever else you want to do. So for the imaging pipeline, so basically there is this the custom-made software which basically works quite well for GMRT data, because GMRT data, one of the biggest issue is the RFI because of the frequencies and bandwidths that you work with. So there is like a multiple layers of calibration, and then so this is all heavily automated. You just give the raw data, goes through the correlation pipeline and produces the visibility data, and the flag cal pretty much removes all the bad baselines and visibilities and produces the final FITS file that you can take it to any of the imaging packages and do it. And this is just one example, and this is that a single pulse from a non-pulsar but detected at a very large beam offset. So in this case the signal was not at a very large offset, but we can detect, the survey has detected this with offsets as large as like a couple of degrees away. So then you can, this is the dirty image, and this is after cleaning and self-cal. So you can get the sub-Jansky signal you can happily detect using the flag cal and imaging pipeline. So once you do that, like I said, that you know where the source is, and so you go and form a sensitive phased array. So the signals, which originally was not easily discernible in the data, but the detection algorithm thinks that that is likely to be a real signal because just seen in all different subarrays. So once you form the phased array, then you can buy back that almost an order of magnitude increase in sensitivity. So that is essentially that crux of the event analysis pipeline. So I will just finish it up. The radio transient, it's a very important area for all next generation instruments. And for searching for fast transients, you have to deal with a whole bunch of problems related to propagation effects and RFI and things like that. So you have a lot of computational challenges. And the high time resolution surveys at Parkes and Arecibo are discovering an increasingly large population of intermittent pulsars. So that is one of the most guaranteed outcomes you can expect from those surveys. And the existing instruments have an important role to play, and the GMRT and the VLBA based efforts are one of your first steps in exploring that multi-station advantage in demonstrating the effectiveness of transient detection. And of course, the Arecibo's sensitivity will be your, the best bet when you want to do targeted searches for finding pulsars in faraway galaxies. And apart from doing this transient detection related things, the GMRT in general provides a powerful test bed for a lot of important methodologies related to other high time resolution science applications as well. And all of this should basically, that give you important lessons and valuable inputs as we are getting ready for next generation radio astronomy stuff.